All right, so let's say that we have a seesaw here, and we're looking at, so we're going to start with what's called point masses on a line. So we've got a seesaw here, and we've got our two people. So we got one person and another person here. And our seesaw isn't perfectly balanced on the center. If you've ever been on a seesaw, you know that you can move the saw, I guess you call it. You can move the thing, the board, one way or another if you have one person over here who weighs more than the other person over there. So like you can usually move it 1 or 2 notches one direction or the other to try to keep it in balance so that it's more fun.
Yeah, I've never.
You've never been on a seesaw?
At the old elementary school, they weren't like
Oh, okay.
No, if you were fat, you just sat there.
Yeah, for real.
And
Okay.
lifted the other person in the air.
Yeah,
So,
and then when you're fat, then you get off, and then the
And then
whole
the
person,
other-
i.e. me, up at the top, is slamming down and
Okay.
break your everything. And
Okay.
better hope you didn't have your legs crossed under there, because when you come slamming down.
Right.
There
You're going to break your ankle or something?
yeah, you're gonna break
Like,
something.
what's the merry-go-round?
Okay. Okay, so anyway. Okay. So if these two people weigh exactly the same amount, then the seesaw is going to balance and they're just going to kind of like hang there, right? If the person on the right weighs more, then the person on the left is going to go up to the top. If the person on the left weighs more, then the person on the right is going to go up to the top, right? Yes, no, maybe so? Okay, cool. But if they both weigh exactly the same, then they're going to stay there. Otherwise, we're going to have this motion that goes kind of either of those two directions. Okay. Now, what's going to happen here is that we've got this kind of balance point, which is called a fulcrum. It's in the center. And about the fulcrum is where this whole system wants to turn. It either wants to turn clockwise, which is around this direction, or it wants to turn counterclockwise, which is around that direction. Which kind of brings in, there's a lot of physics stuff I could get into with that, but I'm going to try and keep it restrained to just the topic of the day, which is moments and center of mass. So like there's a lot of stuff about like something called the right-hand rule and torque, but I'm going to focus just on this. So it either wants to move counterclockwise or it wants to move clockwise, which is what we're going to focus on for the moment. So in general, what's called the moment, so the term moment is going to be equal to the mass times the distance from the fulcrum. So the moment is called, the moment is the mass times the distance from the fulcrum. And the fulcrum is this kind of balance point in the middle.
Is the moment describing which way it's going to turn?
Yeah, so if you create a situation where everything is equal to 0, then it's going to be flat. If it's going to be equal to a positive number, then it's going to want to turn clockwise. If it's going to be equal to a negative number, then it's going to want to turn counterclockwise. Okay, so let's say that we have, so where do I want to move next? So we are going to be doing some stuff with balances probably tomorrow and Thursday. That's going to be what our quiz is going to be for this week. But for today, let's talk about if we have a balance beam here. So we just have like a straight up line, and I'm balancing stuff on this line. And I have a point 0 right here. And I'm balancing different, I'm trying to find a point of balance of different weights somewhere on here. So let's say that I have a weight that weighs 10 of something, and it doesn't really matter what the units are. You can say the units are pounds or grams or cheetahs or whatever you want your unit of weight to be. And I'm going to have this be 5 something away from the or away from the 0 point. Again, it doesn't really matter what the distance of measurement is. So if you want this to be 10 pounds and that to be 5 feet, that's totally fine. Let's say I have another weight here that is 2 pounds, and this is 8, or maybe this is grams, it could be pounds, and this is 8, I don't know, feet or inches or centimeters or something away from the 0 point, from the 0. Was that what you were going to ask?
Yeah, I said I was gonna ask from the 5 or something.
From the 0. And I'm going to throw another little weight in here. I'm going to put it in between those other two. I'm going to say this one weighs 7 pounds or kilograms or feathers or something. I'm going to put it in between the two. So this is going to be, let's say, 6.5 from the 0. Now these are all like sitting on a board, so I want to find exactly where the perfect balance point of that board is going to be. Does that make any sense what I'm saying? So how I'm going to do that is I'm going to take this and I'm going to look at it as if, or at least this is the easiest way for me to do it. I'm going to look at this as if it were a table. The first thing I want to do is I want to find, here are my masses, and these are my distances. So my masses are 10, 7, and 2. And my distances for 10 is 5, for 7 it's 6.5, and for 2 it's 8. You guys with me so far? So first I want to find out what my total mass of the system is. So total mass is going to be equal to 19. And then I want to find out what my total moments are. So the moment of this first one is 10 times 5, which would be...
You wanted it from the fulcrum, though.
So I'm going to count this as the 0 point. I want to do it from 0. So the reason I'm doing it from 0 is to find out where the fulcrum is. So I'm going to go from 0 first to find out where the fulcrum needs to be from this 0 point. Okay? So 10 times 5 would be what? 50. And then I'm going to add that to 7 times 6.5. Is it 45.5? Everybody agree with James?
Yeah.
Okay. And then I'm going to add that to 2 times 8, which is what? 16? All right, so these are going to add together to be 50 plus 45.5 plus 16. So 111.5. Is that making sense where those numbers are coming from? Okay. Now, if I take these two numbers represent, okay, so this represents essentially the total moments of the entire system. This represents the mass of the entire system. This number divided by that number is going to tell me essentially where the fulcrum should be in relation to 0. So this number here divided by that number there, so 111.5 divided by 19, spits back out, I'm going to round that to 2 decimal places, 5.86.
5.87.
Oh yeah, thank you, 5.87. That means that from 0, my balance point should be 5 and then a little more. Now intuitively, does that make sense? Does that seem like it's about where the balance point should be? On the right hand side of the 10, does that make sense? That you should have 9 on one side, 10 on the other side? And the reason that you can have 9 on one side and 10 on the other side to balance that is because you have so much space on this side to make up for the fact that you have more weight on this side, but that more weight is closer to where the fulcrum is. That's why you can have less weight over here, because you have more space for that weight to balance on. Have you guys had this idea before that you can move something if you have a long enough lever to give yourself leverage for it? That's where that term leverage comes from. If you have a long enough lever, you can move something much heavier than you should be able to. And so even though the 2 and the 7 and the 2 add up to be less than the 10, they'll balance with the 10 because they have enough leverage to work out with it. Does that make sense? We'll be doing some physical stuff with this week, so you guys can actually see this in action. But yeah, kind of, sort of. All right. So this is in what's called one dimension. We're only working with this on one direction. Let's take a look at what happens when we deal with this in 2 dimensions. So we're going to have both an x and a y. So let's say that we have a...
What would be like a real world application?
Okay, so there's a couple different real world applications for it. First of all, center mass can help you with a few different things. If you're dealing with a work problem, if you have to find out how much work it takes to move something that's really strangely shaped, if you just find out the center mass of the thing, the amount of work it takes to move center mass is going to be the amount of work it takes to move the entire system. And then also center mass can be used for, like, in complex systems, center mass can be used for balancing things that are more complex. Like, you can balance a really, really complex thing on what its center point of mass is. So, like, that's essentially what we're doing, is we're finding what its center mass is. So, I mean, there's all kinds of different applications for it from, I don't know, the first one that comes to my mind is car stuff. So, like, all those complicated crumple zones that they started adding to cars in the 90s, those are almost entirely based on where the car's center of mass is, which they started being able to find because of computations that they were able to do with more computers that they had in the late 80s, early 90s. All right, so let's talk about this in 2 dimensions. So let's say that we have a plane, an XY coordinate plane. All right, and I'm going to have a point down here called 0, 0. And I'm only going to deal with quadrant 1 here. I'm not going to deal with quadrants 2, 3, or 4. I'm only dealing with quadrant 1. Okay. So let's say I'm going to put some weights. I'm going to put a mass of 2. So this is a mass of 2, and I'm putting it at the point, I don't know, let's call this 3, 2. So over 3 up 2. I'm only going to do 2 or 3 of these. And I'm going to put another mass over here. Let's say this mass is a mass of 1. And I'm putting this at the coordinates, let's do 5, 5. And I'm going to put one more weight on this. Like, imagine it's like a, I don't know, a sheet. Or not even a sheet, like something stiff, like a piece of cardboard that I'm putting these weights on. And I want to be able to find the balance point of it. We'll do one more. And we'll say that this little weight here has a weight of, we'll do 8. And it's at, not 3, 4, 4. And I want to be able to find the center of mass of the system. Okay? So to find the center of mass of the system, I'm going to create a really similar table to the one that I did up here. But instead of having just one distance, I'm going to have 2 distances. One for distance on x and one for distance on y. So I'm going to have mass, and then I'm going to call it distance x and distance y. So I have 2 different columns on my table. Bless you. So my masses are going to be 2, 8, and 1. And then my distance on x are going to go in here. So the one that's 2 has an x distance of 3 and a y distance of 2, which is why I'm calling this 0, 0 down here. So I'm only dealing with quadrant 1. There's no reason to have any like quadrant 2, 3, or 4, because there's no reason to have any negative numbers in here. Like, if I'm creating this quadrant system on my own, I might as well only deal with positive x and y numbers. There's really no reason to create negative x and y numbers.
You don't need that negativity in there.
Right, exactly. No haters. With the 8, the x and y distance are both 4. And with the 1, the x and y distance are both 5. Okay, so again, I'm going to find the total mass of the system. So the total mass in this case is going to be 2 plus 8 plus 1, 11. And then the total moments I'm going to find total.
Do you want to break it up for X and Y?
Right. And so I'm going to do one for X and one for Y. So for X, it's going to be 2 times 3 plus 8 times 4 plus 1 times 5. So it's going to be 6 plus 32 plus 6. So 6 plus 32 plus 6. So that's 44. And for Y, it's going to be 4 plus 32 plus 5.
Yeah.
Oh, did I make a mistake? I did. Super wrong. Okay, so 38 plus 5 would be 43. Mr. Taft. And then down here, this would be 36 plus 5 should be 41. Unless I made a mistake on that too.
Instead of where you wrote 41, it should be 5 first time.
Oh, haha. Good Lord. Okay, thank you. Mr. Taft. Okay.
So then you would just divide each of them to get your X, Y,
Right, and so I do this 43 divided by 11 to get the x coordinate, and then 41 divided by 11 to get the y coordinate, and then that's going to be the x, y coordinate of the center of mass. So 43 divided by 11 is 3, I'm going to round that to 2 decimal places, so 3.91. And then the y coordinate is going to be 3.72, and that's the y coordinate. So this,
3.73.
oh, thank you, 7.3. I'm making mistakes all over the place today. 3.91, 3.73. So that's the center mass of the system. Kind of, sort of? All right. So there's a little bit more that we need to go over, but I can set you guys a little bit loose on your assignment. We'll go through part of it together, though. Your assignment's going to be 5.4. I'm going to pass it out to you guys. I don't even need to give you the page number because I'm just going to pass it out to you guys. It's going to be 1 through 7 on the page I'm going to give you right now.
Just like what we did here, you just had to do it.
So there's a tiny bit of a twist on questions 1 and 2, and 3 and 4, and I'll go over the twist with you guys. And then 5, 6, and 7 are kind of cool too. But I mean, like I say cool, you probably would use a different adjective. Demented.